hyperfine transition, it's 2 orders of magnitude smaller than for this 2s2p transition. So the transition probability goes with a square. So it's like we have to somehow manage to increase the laser fluence by maybe 4 orders of magnitude somehow on our atom. So that's the one of the big challenges of this experiment this time. So this is my only pseudo theory slide. I think we've heard this enough. Essentially, we're measuring the left side. This is calculated. This is we make a statement about all the stuff that is hard to calculate. Okay, to keep it short. Yes, so we do this at PSI because PSI has this one of the most intense low energy muon beamlines in the world in the nice experimental hall at PSI. And since I want to talk about different elements of the experiment, I think it's nice if I give a short summary again of the experimental sequence that we follow to hopefully measure this resonance. So we come in with a muon beam, low energy, individual muons coming in, so at a rate maybe 500 hertz or so. They cross an entrance detector, and the signal from this entrance detector triggers the laser system then. The muons are stopped in a very thin, only 1 millimeter thin hydrogen gas target, cryogenic temperature, 22 Kelvin, and somewhere 0.5 bars maybe. And they essentially, a muon comes in, replaces an electron, creates muonic hydrogen in a very highly excited state. And it quickly thermalizes to the surrounding gas temperature. Here you see a plot of the average kinetic energy of such a muonic hydrogen over time. And let's say, so it de-excites from a very highly excited state down to the 1s ground state, and then further to the 0 state. And after, say, 1,000 nanoseconds or so, we incouple the laser into our target region. So there's an optical enhancement cavity here surrounding the whole target region because we don't know exactly where the muonic we could maybe drive the transition if equals 0 to 1. And now comes the trick of the whole detection system, because you can imagine we will never see the decay of this transition, right? The muon just decays before. So what the trick that we employ is that kind of similar to the FAMU, it always reminds me, when this excited muonic hydrogen atom collides inelastically with the surrounding gas molecule, it de-excites back to the 0 state, but it retains kinetic energy. Here you see a plot of the kinetic energy here on the x-axis, and then the mean free path. And so if our muonic hydrogen atom, which was collisionally de-excited back to the f equals 0 state, retains this kinetic energy, it's much more mobile. It has a longer mean free path, and it can then diffuse through the target, so through the hydrogen gas to the target walls. You see here a plot. The 0 would be this 1,000 nanoseconds. So 200 nanoseconds after the laser pulse, we expect here the number of muons which made it to the wall to be maximal. So it's kind of a histogram that you see here, and it sits on top of a larger background of muonic atoms that simply diffuse to the target walls without being laser excited. So that's just, in our scheme, that's just the way it is. We will have this diffusion background. In a very high target, in a very highly excited state, and the decay cascade, during this decay cascade, muonic X-ray, muonic gold X-rays are emitted, and these X-rays we actually detect. So in the end, what we do, we scan the laser frequency and we count these X-rays that we detect. Okay, that's the indirect scheme that we want to use. So we simulated a little bit how do we expect the resonance to look for our conditions? And the different curves are different temperatures of the gas. So orange and blue would be for 22 Kelvin, green and red would be for 50 Kelvin. But essentially, we expect a line of about 250 megahertz line width, and the broadening of this line is mainly due to Doppler and then also the laser line width itself. And yes, if we take the most of the literature values that exist, we come up with a conservative search range of about 20 gigahertz in each direction. That means that we will have to scan about 300 points, and yeah, probably we can do it in one beam time at PSI, but it will take a time just to find the resonance, of course. Okay. Yes, so now very briefly about this detection system. Where do we stand here? The atom, the excited diffuses to the wall, creates the signal, lots of X-rays. Maybe even the muon spirals down into the gold nucleus could create neutrons or gammas, whatever. But we can detect them then with our X-ray detectors. I talked about the diffusion background that we have, but we have also this Bremsstrahlung problem that we also briefly touched in the FAMU discussion. So if a muon decays, the decay electron might pass through the target mechanics, creates Bremsstrahlung, and okay, we might mistake it for a signal. So what we do to fight this is we introduce a thin plastic scintillator between the BGO X-ray detectors. So if we detect energy, the electron will deposit significant amounts of energy in this scintillator, while the X-ray doesn't. And that's the trick. So we can, if we detect energy in the scintillator and in the X-ray detector in coincidence, then we know it must have been an electron. Okay, so we can cut on the energy deposited in the scintillator. We had a test beam time in 2019. This was the big part of the PhD thesis of Laura Synchronite. Yeah, and we concluded that we are able to, or let's say we make a misidentification only in 9% of the cases, so to speak. So that should be okay for our experiment. We can live with that. Yeah, this was extracted here. The uncorrelated was, we could also measure that, and the diffusion is mainly simulated for the target parameters. So this means that our background is still, the background rate is still much higher than the signal rate, but okay, this means that it just takes time for each laser frequency setting. Yeah, and then the other absolutely crucial part of the whole experiment is this enhancement cavity. So you can imagine designing a cavity that works in cryogenic temperatures with this annoying constraint of having only a millimeter diameter, a millimeter here in width, at the strange wavelength of 6.8 micron, where we expect the transition to lie. It's not an easy task. So actually the biggest part of the thesis of Miroslav Marjalek went into this. But okay, he came up with a prototype. So a toroidal cavity, the laser is incoupled through a tiny slit here, bounces around then several hundred times, depending on the coating quality. And then you see here, for example, a simulation of the expected fluence in this cavity. And we're actually interested in the target volume. What's the mean fluence that we reach in this target volume, right? We average because we don't know where the muon will stop, somewhere there. So we're interested in the average value. And he was able to measure for his prototype, so the toroidal shape, but he also investigated a two-piece mirror, which is a little bit easier to manufacture, easier to coat with a dielectric coating, because the toroidal cavity was just bare copper. And you see that for his two-mirror cavity, the extracted reflectivity was above 99.9%, which leads to some value, 2.5 joule per square centimeter average fluence. while the toroidal prototype with the bare copper was performed less. But you also see that if we manage to coat this one nicely, then we can massively outperform. Okay, so that's we're currently investigating. Maybe we can put the dielectric coating in this. So that's an active area still where we're investigating. And then comes the part where I did my PhD on the laser system. How do we provide the pulse? Very briefly, the requirements for this laser system. So it has to be very fast because we're dealing with muons, they decay. It has to deliver a large pulse energy at this strange wavelength, 6.8 microns, and of course, single tunable to perform spectroscopy. The combination of all this means that you cannot buy it. Unfortunately, we have to build it, and that's the idea. So I don't want to go too much into detail about the whole thing, but conceptually, what do? We start with an injection-seeded thin disk oscillator at in the near infrared, 1030 nanometers. That's proven high-power laser technology. And then we further amplify this even in a multipass thin disk amplifier to about 300 millijoule pulse energy. This was my PhD, essentially, the thin disk laser part. And then we take one branch where we go into OPOS and OPAS, where we create 3.1 micron radiation, and in the other branch we do the same with and reach 2.1 micron radiation, and then finally a difference frequency generation stage where we create the 6.8 micron, and we uncouple it into Mirex cavity. That's the plan. So just to show you a sketch of how this injection-seeded thin disk laser looks like, we come in with a seed here, and we use the interplay of a Pockels cell, a lambda quarter plate, and a high voltage on this Pockels cell. We can rotate the polarization, and then everything is reflected here. The pulse builds up, and if we're satisfied after a certain amount of time, let's say 600 or 650 nanoseconds, we apply or we reduce the voltage again on the pocket cell, the polarization is rotated back, and we shoot out the pulse. So after 650 nanoseconds, we reach about 35 millijoule. That's pretty fast, I would say, but not enough energy. So and then we also measured the chirp in the laser pulse, and so we did this by frequency shifting the seed and then superimposing it with the oscillator pulses, detected the beat signal on the fast photodiode and quadrature demodulated it here, and we could reconstruct the pulse nicely. And I would argue that the chirp is basically 0, so we don't have a lot of chirp. That's very nice. Yes, and then to increase the energy further, we have this multipass amplifier, which I sketched here. The goal is to go as many times as you can over the disk, where every time it's amplified, let's say about 10% maybe on each pass. But I just want to briefly mention that we have a new concept for this. It's not just stupid back and forth propagation. We want to have really stable output beam parameters. So the way how we achieve this is that on this part here, with the mirror array here, where we really individually guide every beam, this, if the beam does a round trip through this part, it's optically Fourier transformed. And I don't have time to go into this now, but turns out this optical Fourier transform stabilizes the output beam parameters against thermal lensing. So that's very nice. The beam quality is excellent then, and doesn't really change for a large parameter range of what happens on the disk. And to make the whole thing compact, we image the beam from the end mirror here to the disk, so all the passes go over the same optics. That's quite nice. So this is really a new way to design multipass amplifiers, and we saw that it works rather well. Even under full pump load, the beam profile almost didn't change. So we really go from cold state to full pump state. Beam just stays the same. Pointing jitter is very good, less than 3% of the beam waste. And okay, we reached about a little bit more than 200 millijoule, not quite enough, but we're pretty confident that we can scale this a little bit further. Yes, and then just very briefly, a word on the OPO status, we're currently setting these up. So I just show you a sketch here would be the crystal where we create the seed. So it's also in a seeded OPO. Instructions. So thank you very much for your attention.
Thank you, Manuel. So, any question?
Detection, no, the detection scheme. Yeah, no, where you show the extra energy. Yeah, there, maybe, yeah. So my question is, you are only taking into account this extra energy from the photon emission, right? And that's about, I just calculated, it's about 2000 Kelvin or so of energy. And your sample is at 20 Kelvin, right? Your gas.
Mm-hmm. Yeah.
But then you also have the
people who probably know.
Yeah, they consider the process from the recoil of the absorption. You are in the direction that doesn't matter, maybe too much for you. I don't know.
I mean, you
I'm not an expert either, but like the absorption of photon is at 6.8. Yeah, but well, we have to really reread the paper, but you are still on the thermalization. I mean, it washes out. It's yeah, but then it's after the excitation that after a delay, and this is like more stable. You will see it's like the when it flipped down. Yes. It's just the timing. Well, yeah, what is really important, as Manuel said, is like we are really in a timing detection. First,
yeah,
okay, we have a coffee and
because the absorption process also gives you a recoil the same size.
So, yeah, definitely, yes. Yeah. But it's cross section is what is important. When you are in F1 and F0, you don't have the same cross section, so you don't thermalize the same, and so on and so on. I can have a drawing after.
Thanks.